Hello, everyone. Welcome back. All right. So this time I'm going to talk about dissociating artificial intelligence from artificial consciousness, or said more kind of colloquially, I'm going to talk about computer consciousness and what IIT thinks about it. Perspective from integrated information theory. Before I get started, I want to kind of give credit to my colleague, Graham Finley, who did a lot of this work with me. And also created this slide deck, which I greatly appreciate from him. Okay, so the talk is going to kind of be split into two parts. The first part is, why or how do we study artificial consciousness from the perspective of IIT? This is kind of, philosophy of science almost, like why is IIT the right tool for this? And in so I'm going to there'll be some review of some IIT basics. So if you're like super steeped in this, it'll be some overview, but I think there's some value in kind of reiterating some of the core points. So I'm going to do that. And then the second half is going to be kind of, okay, let's now apply the formalism that we built and draw some conclusions about artificial consciousness. Okay, so most theories of consciousness take the extrinsic perspective. Right, we want to start from a physical world, whether that's space-time, mass, charge, or from behavioral correlates, what can I do when I'm conscious, functional correlates, neural correlates of consciousness, right? This is the dominant scientific view on most things, but even for theories of consciousness, this is where most begin. And then from that physical world, we try and answer the question, well, how is this physical world going to give rise to experience? I'm going to go to my physical world, I'm going to search through it, I'm going to look and find consciousness, I'm going to find phenomenology, it's hiding in there. And then so we go to Leibniz and his metaphor of the mill. And this connects to the hard problem. It's a little bit older and a little bit more kind of fanciful way of doing it, but so when Leibniz presented this, and I should say, this is like a third person recount of this. I'm stealing a little bit things I've heard Julia say before. But so Leibniz says, okay, well, imagine there was some machine, the brain, and that inside that brain, we would go and we'd find consciousness. So let's take that brain and we want to kind of blow it up and make it big as it's and we can now walk into it like it's a mill. And when we walk into this brain, all we're going to find are parts that push one another around. We're going to find mechanisms that do work, but we're not, in neural terms, we're going to find neurons, and we're going to find action potentials and neurotransmitters, but we're not going to, all of a sudden find this colors, sounds, experiences. They're not going to be in the mill when we look. And you can take this kind of, Leibniz was from a long time ago, more mechanisms and functions, but you replace this by neural correlates, or, you expand the brain, you go inside, you're going to find attention, you're going to find perception, you're going to find memory, but you're not going to find consciousness in there. Just because you can walk among the functions, you're not going to, all of a sudden, it's not going to reveal itself to you. And then so we come to IIT and IIT's intrinsic perspective, its consciousness first perspective on the problem, which, instead of starting from physics and trying to squeeze phenomenology out of it, we're going to flip the script. We're going to start from experience, our own phenomenology, which exists immediately and irrefutably. So that's now the starting point. And we're going to aim to account for it, its presence and its quality, in physical terms. So we start from the phenomenology and then we go and we try to account for or explain it from the physics as opposed to starting from the physics. And of course, for IIT, as we've heard, physical is operational. It's cause-effect power. It's observational manipulation. We go and we experiment on this physical world and we try and explain consciousness. So for IIT, we identify these essential properties of consciousness. These are the axioms, but here they're kind of described. Each axiom kind of has its kind of synonymous term that we use. So these properties that are true of every conceivable experience, every experience is intrinsic. It's for me, it's specific, it is the way it is. It's unitary, it's one experience, it's not two. It's definite, it's not less than it is, nor is it more than it is. And it's structured. There are parts of it, and those parts are related. And we take these essential properties of every experience, and we translate them into properties of cause-effect power that are properties of the physical, the operational physical universe that we're going to explore and experiment on. And then we're going to put together a framework for assessing these properties. So we observe, and we manipulate this external world. We reveal its cause-effect power, and then we can kind of say, well, is this cause-effect power intrinsic? Is it specific? Is it unitary? We want to find the properties of experience mirrored in the operational properties of the physical world. And so here's the idea. So all phenomenal existence is intrinsic, specific, unitary, definite, and structured. And so we are accounting for this phenomenal existence in physical terms if the substrate's physical existence is intrinsic, specific, unitary, definite, and structured. I kind of tricked myself with a second picture. I thought I needed to go back and say that, and I ended up saying it twice. And this process kind of has a few steps to it. I think it's easy to kind of separate the kind of first, is it the substrate, and the quantity, and then the quality. First, is it conscious? And then if it is conscious, in what way is it conscious? So we start with okay, is it conscious? We find the substrate. And so this is kind of, okay, presume it's in the brain, and we can draw a border around it. So this is the substrate of consciousness. And so we have the phenomenology is intrinsic, specific, unitary, definite, and structured. The cause for the physical existence should be, that means the cause-effect power should be, and that translates into, is it a maximum of integrated information? We go to this physical world, we measure integrated information everywhere, and we search for where it is maximized. And once we find it, we call that a complex. So we go and we search for the complexes, and presumably each of us conscious observers in the room have a complex, again, probably in our brain. I assume it is, but that's not required by the theory. That's just, let's say, empirical evidence.
Are you not using an equal sign over there intentionally?
Here? No, I think this is like the start. It's like this equals this. Oh, this is equivalent to this equals this equals this. Okay. And then once we found the complex, now we want to talk about the quality of experience, what it is like to be this conscious being. And so that's where the structure comes in. You'll see that everything here, when you kind of flesh out the framework, this is, so phi is intrinsic, specific, and unitary. Definite is where you get the maximum from. And then that's why it's kind of grayed out here, structured. And then here's the structure that comes out on the quality part. And so because we want every aspect of experience to be explained for in the physical, the quality of the experience must also be accounted for by the physical, the operational physical, and that is in terms of the structure of its cause-effect power, which we unfold from the complex in terms of distinctions. Those are kind of like individual pieces of cause-effect power, causes and effects within the system, and relations, how they kind of overlap or are kind of common causes and common effects.
I have a question that is not very clear to me what a causal distinction is, insofar as this is the mechanism and the purpose, or what we call the mechanism is mostly like a label for that specific bundle of cause-effect power, which is basically a link between a closed purview and an effect.
Yeah, so I think when we use the term distinction, especially if you're like in the mathematical framework, you've got the mechanism, which I would say is the piece of the substrate that we're talking about. So a specific neuron or a specific group of neurons is the mechanism. And then its cause and its effect, the causal power, those are the purview. So it will have a specific set of neurons that it affects, and it will kind of specify them into a state, and it will do neither more nor less neurons that it specifies into that specific state. So the causal power is really like the quality of it is all about what is the purview and what is the state. And then the mechanism is kind of like, what's the physical thing that supports it within the complex? And all together, we bundle those into, that's the distinction. It's both kind of a description of what supports it and what it is in terms of causal powers.
You can label each mechanism, let's say with a smaller capital letter, right? And in a way that is necessary though to really understand this particular architecture. It's not the structure itself because you have to take into account what the operations are of each of these neurons, right?
So I would say that, I mean, we label them because that's convenient. That's how we have to do the math. But ultimately, it's more of like I'm going to be kind of slightly imprecise here, but the topological structure of this kind of like graph or simplex that defines what it is. I mean, if A is just A and B, like if I switch A and B, that shouldn't be meaningless. Or on is 0, or on is 1 and off is 0. Those are both extrinsic things. I should be able to wipe those out and replace them by Greek letters or, different obscure symbols. That shouldn't matter, right? So you kind of, to the question of how do we compare cause-effect structures, I think the first step is to wipe away all of these labels. Now, you do need kind of an internal consistency, right? If neuron A, its effect is making neuron B fire, and neuron C's effect is making neuron B fire, of course, you have to know that they're doing the same thing. That's how you know they're related. So the sameness is important. But whether I call that firing or some other word is irrelevant. And what it means for neuron B to be on and macro column X to be on might be different, and the onness doesn't need to be anchored.
In the sense of to read with what Pascal told in the day one, optimal transport.
Yep.
What you're saying is basically without the final evaluation work, but just quantifying how similar this structure is using the one transport, that part is more important.
Yeah. That, to me, that's where I would start. If you said, okay, after this lecture, go start a project to compare cause-effect structures, that's where I would start. I would start out as optimal transport and then build from there. I mean, they're not exactly, but if you want to kind of have a mathematical object that you kind of make analogies to, that would be a good place to kind of start. Are they simplified complexes? Okay. So kind of big picture for IIT, an experience is a cause-effect structure, and specifically the cause-effect structure unfolded from a complex, right? And this is what we call the explanatory identity. It's how we start from phenomenology, we operationally go to the physics, and we try and explain the phenomenology, right? That's the whole kind of picture there. We start from phenomenology, do the operational cause-effect power, operational definition of the physical, and then see, can we find the properties of the phenomenology in the physical? And if we do, we're essentially explaining how the physical is supporting the phenomenon or how it is underlying it in whatever way it does. And because an experience is a cause-effect structure, that implies it is not a neural activity pattern, as we just saw with Will's talk. It is not a process or a code or a computation or a function. It may correlate with some of these things in some situations, but it is not fundamentally that. Okay, and so, yep.
I get well the equation of neural activity, but when you say a process, I'll assume that your cause-effect structure also has implies duration, right? Constant time, and therefore could still be a process.
So I would say that one experience is a cause-effect structure. Yes, of course, there are different experiences, but there's nothing that, the relation of experiences across experiences is not fundamental to the one. So yes, extrinsically, we could describe the flow of experiences and how they change, but that's not fundamental to what an experience is, at least for IIT. This kind of dynamic kind of quantification or qualification of experiences is not fundamental in IIT. You could have an experience, you wake up, you have a first experience of the day. there's nothing before it, so a previous experience can't be kind of.
But I think what you are saying is about in particular now, the current state, how its structure is determined through its relation to one past and one future, and then considers the two updates as a microcosm process, which usually in the process theory and other type of people talk about process as process, then that's a kind of process, right?
So I guess, so of course, causal power kind of manifests as updates or changes in things, and you could define a process that way. So in the same way, like, like microfunctionalism, you can describe functions at the finest possible atomic grain, and they kind of, as you get more and more precise, they almost end up being causal power in the limit of kind of tiny little functions. And so, but the core is it's always causal power. And if you align your definition of process or function to basically overlap with causal power, then there is, of course, a linguistic sense in which that's true.
Yeah.
But it's the causal power, which is the fundamental thing. And whether, but if I say function, that most of the time doesn't align with causal power. And if I say process, most of the time that doesn't align with causal power.
Maybe I'm wrong, but the way I think about it is between processes, you have states. And so the people that think processes is consciousness, they put it between the states. But if you think about my mathematical intuition, what you do with a TDM is you look at what's between the processes. It's a complete shift.
So there we go. We're going to start from phenomenology. We're going to operationally define physics, and then we're going to try and use that operational definition to explain phenomenology. And so only after we do this can we start answering questions from physics. Is this thing conscious? If it is conscious, in what way is it conscious, right? If the loop is complete, now I can go in and I know how physical things support consciousness. I can start asking and answering questions. And so here's how the framework goes. So I've started from phenomenology. I've built my theory. Now it needs to be validated. And crucial here, this validation is in humans, healthy adult humans. I would say you also want to avoid kind of places where we get into huge arguments about what was actually observed or actually perceived. Like if you've got like at threshold stimuli where different people have different opinions, you kind of want to stay as kind of strong evidence as you can, kind of where we have the most kind of consistent agreement about the phenomenology. That's a great place to start. We want to validate in humans. This dashed line back, of course, the theory is not immutable. If the evidence suggests we need to go back and tweak, that's part of the process. But we validate, and validate is on predictions and then testing. And a really valuable thing about IIT is that it makes predictions. It also makes counterintuitive predictions. And in some sense, the validation has, the more counterintuitive the prediction, the more the validation kind of builds your confidence, I'll use the word, building your confidence in the theory, right? If you have a very obvious prediction that everyone thinks is true, then it doesn't really build confidence when it holds up. Okay. And then finally, after we have built the theory and validated the theory, then we can extrapolate. We can ask these questions about, is this thing conscious? And we can extrapolate to the hard questions, right? Whether that's, computers is obviously what I'm talking about now, but, babies or fetuses or octopi or organoids in a dish, now we can ask those questions, and our kind of, again, our confidence in the answers the theory gives are directly linked to our, how well the validation process has gone. If there's zero validation, you can still do these extrapolations, but you don't have confidence in them yet. So the more validation you do, the more confidence you have in the inferences or the extrapolations. And so that's kind of the end of this story about, okay, why is IIT the best kind of theory for answering questions about AI consciousness? I'm going to use this word. It has maximal inferential power. It has the most power to make these inferences. And I'm not going to elaborate that. I'm going to have some prompts about that in my kind of future projects, some things to think about for the students on that.
Maybe it's a good time to mention the conversation we had at lunch yesterday when I was asking about, the actions that IIT has produced, which is obviously studying human experience, and we're using causal effect structure to kind of validate that there's an explanatory intensity between orthogonal experience and whatever substrate we're looking at, and whether there's an issue that if we do look at some other entities and we haven't thought very deeply about the nature of their phenomenal experience, that, do they all have the exact same maximums? And even if they only had a subset, maybe IIT would not show that they're conscious, but,
Yeah. So just in case anyone can hear, the question is, well, what if dog consciousness is fundamentally different from human consciousness, and then it doesn't fall within this? Well, I would say, well, then you use the word consciousness twice, but probably that's not consciousness. And if there's something that could that we would want to kind of just in language describe as dog consciousness, but it's somehow fundamentally, it's lacking essential properties of human consciousness, I would say I don't think we can study that. I think that, really puts it beyond our reach in terms of what we could do if we have no third person access to it. And then now we have no first person access to it. So what it may be, but why bother? What could you explain from such a proposition?
I think you could show that, if the IIT showed that dogs aren't conscious, that would more invalidate IIT than dogs being conscious. Probably millions of people around the world feel about their dogs.
But consensus is not a good friend.
Yeah, so
Consensus is not the best metric for.
No, but
that's sort of confusing, what you want in the end and what it is, right? If the conclusion of this is totally something that you don't like, that's what the consequence is.
Yeah. Well, I guess it's just for me, all of our discussions with consciousness are always extremely human-centric. And again, I find it mostly seems to be between researchers a psychological preference, whether you decide only humans are conscious and then prove case by case that everything else is, or else that you have a preference to believe that not all things are conscious and maybe the degree to prove that they're not. And I don't really see any principle or reason that we might decide it.
It's complicated issues, I think we should.
yeah, we'll see how much time I've got at the end of the talk. I have things I would say about that, but I agree, we've derailed the whole thing. Okay, so there's my prompt slide. So this is kind of like for those of you who are interested in the philosophy of science or more like the science of artificial consciousness. So what is meant by inferential power? These are just kind of like thought prompts. Why does IIT have maximal inferential power? And what are the concerns or reasons for reduced inferential power in other frameworks? So for example, even though I refuse to respond just there to you, let's say I take a computational functional approach in which the behavior of my dog makes me feel like it's conscious. Why might that be a position with reduced inferential power? That's bring it to the discussion. I'm gonna stop on this for a second. So my background is in statistics, and in statistics we have this notion of inferential power, but it's a little bit different than what we say here. It's we say statistical power, and it's like, see, you have a hypothesis and then you have data, and it's the question, well, how much power does the data, in terms of not the actual values, but in how I collected the data, the design of the experiment, how much power do I have to make a strong conclusion, to reject a hypothesis? And when we do statistical inference, I'm just going to kind of say some things and then they maybe help from this. There's two kinds of errors you can make, right? So you have a confidence interval, right? You say, okay, I want to know the mean height of humans, and I collect a random sample of all of you and I measure your heights, and I do my t-test, my normal distribution, however it's normally distributed, and I run my t-test and I get a confidence interval. 95%, mean height is between these two values. Well, I can make an error, which is said, well, I have 95% confidence, which means 5% of the time I am going to be wrong. And that's due to the randomness, the probability in the process. But the other kind of error we make is what we call a study error. It's in the design of the experiment. And that's, I think, what's important here. So in that case, maybe you all as consciousness-centric researchers somehow fundamentally differ from the population at large. And by doing a non-random sample in which I have a biased sample of people who came, you know, to this summer school, I am fundamentally not studying a generic property of the population. That's the statistical version of this. So when you think about how the study is designed, are there fundamental ways in which how you approach it, which might lead to systematic wrong answers? Okay, so now let's move on. So that's how IIT addresses the problem. That's the kind of the research program and why I think it's the right thing to do. But now we can go on to artificial consciousness. So the question is, does artificial intelligence imply artificial consciousness, right? This is the Turing test. If you pass it, should you be conscious? If ChatGPT develops to the point where we think it's got all of our intelligence, do we also ascribe it all of our subjective experience? So if a computer were functionally equivalent to human, having the same cognitive abilities, would it experience sights, sounds, and thoughts as we do? Or, taking computers out of the more general form, does functional equivalence imply phenomenal equivalence? Does a system that can perform the same functions necessarily have the same subjective experiences? Yep.
Discussion with people back home, function of equivalence, and this is very, very ill-defined. Function, which actions are relevant. This detection of brain activity also function. This is very slow.
So I will give my definition. We'll get to the example in a few slides, but I acknowledge, yes, there are many. And so going back to the point that, you know, I could define functional equivalence as having the same cause effect power. And I don't think that would be a crazy, because functional equivalence is so ill-defined, that would be, you know, within the realm of a reasonable definition, but that's obviously not the one I'm talking about here. It's more of like a human behavior functional equivalence, or maybe a, you know, I have memory and I have awareness, perception, things like that, but not that, oh, every single neuron behaves exactly this way to each of these inputs, because then I'm talking causal power. Okay, and so the claim here, just kind of reaching back, that answering this question, does functional equivalence apply phenomenal equivalence, can only be done in a principled manner on the basis of a theory of consciousness that is grounded in phenomenology. So that's it. You have to start from phenomenology. It's kind of like a construct validity. If you don't start from it, how can you be answering the question in a principled manner? And then we have to translate them into operational terms. We have to do the validation on healthy adult humans. This goes to your question. So where does the evidence come from? What's the data that can be considered evidence for or against? Is, you know, healthy adult. So kind of, you start at humans, that's the strongest data. And the further you go away from your first person experience. So for me, the only true data is my own experience. And then I make the leap to you, and that's a very kind of acceptable leap scientifically that kind of everyone who studies consciousness says we have to do, or else we're kind of lost. But the, you know, once you go to the bigger you make that circle in terms of what you accept as data, the farther you move away from kind of a valid construct or like real evidence of consciousness. And then we extract. Okay, so to ask if functional equivalence implies phenomenal equivalence, we want to take pairs of systems that do the same thing and then ask, are their cause-effect structures the same? So we're going to do this in a toy model. So here's our reference system. It's a small system, PQRS, it's in a state, Q's on, S is on, P and R are off. It's got a transition probability matrix. And I apply the integrated information theory framework. So I compute system phi of the system, but all of its subsets. You know, if I look just at P, it's got a 1 bit. If we look at QRS, it's got 0.42 bits. And in this case, the maximum is PQRS, which has 1.51 I bits of integrated information. So the whole 4-unit system is a complex. There's its unfolded cause-effect structure. It's got, I don't know the number off by heart, and it's not on there. It's got a bunch of distinctions, I think 15 or 13 or 15, I think. And then it's got a ton of relations among them. Lots of the distinctions have large purviews. And as a result, we get a big phi value of 391 IBITs. So these are not big phi values, right? These are not the really crazy cause-effect structures you see when we're kind of imagining what a human one looks like, but it's enough to make the point, right? And then we go from there. Okay, so this is my target system, and now I'm gonna have a computer that is functionally equivalent to that system. Yes.
Yes, from the previous slide, maybe you will explain it later, but I want to just ask, for example, now we have this cause effect structure. Can we already interpolate what it feels to be like this for units, or?
No.
But what we need to say something about it.
So this is, the space story, the time story, the like finding what a cause effect, this mapping between phenomenology and cause effect structures, that needs to be done a lot and a lot more and expanded. And then once we kind of get a really good, I think the cliques Matteo talks about, these kind of tiny substructures that might look something like this, might be a good way to eventually say something, but what it feels like to be something like this, I wouldn't speculate or say that we're anywhere near such a thing.
But, and to be clear, for the argument you're making, it doesn't matter at all.
No, it doesn't matter.
This argument.
Okay, so I make this system. Two claims here. One is that this is a computer, and two is that it's functionally equivalent. So I'll start with the functional equivalent point. So my 4-unit target system, PQRS, will go through these states, with color-coded orange to light blue to greenish to yellow to dark blue to red or dark orange. I don't know. I'm not. I think if I go through the relational structure of color, you'll find me to be anomalous. And then I have my computer here, and here are my kind of neurons here, the things that are doing the functional equivalent. So there are a subset of units, and these units will go through the same sequence of states at a consistent kind of temporal magnification. So I will spend 8 micro updates in the orange state, and then 8 in the light blue state, and then 8 in the green state, and then 8 in the yellow state, and this will go on indefinitely. So that is the sense in which these are functional equivalent, that if I was to, redefine states over 8 time steps, they would go through the exact same sequence of states indefinitely. It mirrors the function of the system. Okay. And then, so the other claim is that this is a computer. So this is a toy computer, but it's got a lot of the fundamental features of a computer. It has a clock and frequency divider. It's got a program. It's got a CPU or a multiplexer, an ALU, arithmetic logic unit. And it's got data registers that hold on to what I need. And then it's got the kind of the output of the data register. And so just quickly how this works. So it's got a current state, and then this is the program. The program says, okay, given the current state, this state mixes with this line here and says, do I turn on or not in the next step? So let's say you're in the middle of the process. At some point, this unit will come on, and it will open the gate here, and it will let through the next line of the program. And then that line of the program will interact with this line of the current state, and they will make a decision, yes or no, should P prime be on in the next time step? And then it goes here. This is AND gate, or these are OR gates, I think, or negated AND gates, but if no, they're AND gates, and then this is an OR gate. So if any of these say it should go on, it goes on, and it comes here, and it waits right here, and it'll just be held here. And then Q will be computed, and it'll be held here, and then R will be held here, and S will be held here. And then we'll get to the end of the clock and frequency dividers, and it will open the gate, and it'll say, okay, everything that's been kind of stored here can propagate up. So it just does the computations, it holds them, and it lets them go forward. So it's got kind of like features that you expect in a computer, like the modular parts that engineers design. That's how humans design computers, and that's how it works. Now, there's no claim that all computers are exactly like this, right? This is a reasonable computer. That's what we want to say. Okay, so now what happened? Yep. So there's like 55 units here. Yeah, so yeah. So if you took the TPM of PQRS and you did it at like a tau of 8, and you didn't do any manipulation or observation, or like you didn't do any kind of causal, like marginalizing background conditions or anything, If you just took PQRS over a tau of 8, you would find the same TPM. But that is kind of ignoring the causal structure among them. So there's many ways you can go from a micro TPM to a macro TPM. There is a way to do that, but what you'll see, I'll say, is that that way wouldn't align with an appropriate way to quantify the cause-effect power of the system.
So again, is that your definition of functional equivalence, right? TP, if you only use as a TPM, the subsystem, if you evaluate exactly the same TPM, it is
Yeah, so these two are functionally equivalent if up to a certain mapping, they have TPM equivalents. That could be a way to kind of formalize that. Okay, so now I take this computer and I run through the algorithm, and what we find is we do not, the whole computer has phi 0. This is because it's feed forward, although we do have a version of the computer where we put feedback in just to kind of prove that that's not a trend. We're not saying, oh, it's feed forward, that's the only reason. No, you can put feedback in. It doesn't meaningfully change the conclusions. So the whole computer has phi 0 because it's not integrated. And what we find is we get these a bunch of small complexes. So each program is a copy loop. It's a very stereotyped cause-effect structure that looks like this, 4 distinctions and some minimal relations. And then all of these units with self-loops form monads. So they have these very, one distinction with a cause and an effect. And that's all we get out of the cause-effect structure for the computer. So our original cause-effect structure had 391 ibits. Here, each of our programming lines. So if you have an n-bit computer, you have 2 to the n programming lines with less than or equal to 6 bits. So if, depending on the state of the frequency divider, you can break the causal chain here. So sometimes it has the full 6 ibits and sometimes it has less. This is an upper bound in what they have. And the same for these monads, they have an upper bound of 2 ibits, but depending on the specific state of the computer, sometimes they have a little bit less. Okay. And then this, if the state of the target system changes, the complex and its integrated information also change, and its cause-effect structure changes. So here are the 8, or no, there's 16 possible states. Here I'm not sure here exactly why there are more states. I didn't realize until exactly this moment, but here are 10 different states that PQRS can go through. And you can see that, so this state, once you're in the state, you stay in it, and then we have this sequence of states. Maybe the others just don't dynamically occur, and that's why they're not being presented here. But you can see the cause-effect structure changes as you run through this dynamic sequence of states. So for the target system, whose state changes, like you or I, as our state changes, our experience changes. However, for the computer, as we run through the simulation, this doesn't change, right? You still have, I mean, it can very minimally change with this 6 bits going down to 4 ibits, or this 2 ibits going down to 1 ibit, but basically it always has the same stereotyped, very insubstantial cause-effect structures. And so for the target system, the cause-effect structures are changing dynamically. For the computer, they're not. Yep.
I mean, I'm relatively unfamiliar with the whole functions, but why is the one not?
So bases are third order relations. So that means there's 3 distinctions that are related. So here only pairs of distinctions are related, whereas in all the other ones you have at least common overlap amongst 3 or more distinctions. And these are always, they only show up to third order. There are fourth, and well, in this case, there can be higher orders, but we're never visualizing those. They're, too high dimensional. What do I have for time? Okay. Okay, so that's kind of, I mean, I don't think anyone is really too shocked that at the micro level, the computer's cause-effect structure doesn't match the one of the target system. So the natural question is, well, what if I look at the computer at higher levels of organization, right? This is basically my talk from yesterday. For IIT, we don't want to find the micro level cause-effect structure. We want to find the cause-effect structure and the complexes at the grain that maximizes integrated information. So I might want to, call each of these program lines macro units, I might want to call each data register a macro unit, maybe the multiplexer is a macro unit. Maybe I want to study it the way the engineer designed it, right? And so how do I do that? Well, I presented the talk yesterday. This is the framework. So we want to now apply that macro micro framework that we talked about yesterday to this computer and see where does phi maximize. And I'm going to give a qualified conclusion here. So in the paper, the kind of like the theorem or the result that we say is there are no functionally relevant macroings of the computer that recover the simulandum's cause effect structure. I will tell you, just from my kind of intuition and experience with the whole framework, there are no macro systems that are in any way interesting or maximizing phi, but the actual framework is so difficult and like computationally intractable to deal with that it's very difficult to kind of like precisely in a rigorous mathematical way write this down. But there's none. But we can prove explicitly with like ruling out every possible case in this massive tree of possible options that if you assume that your macro units should somehow be related to the function of the computer, basically meaning that there are macro units whose states are defined by P prime, Q prime, R prime, and S prime. If I start there, I can say there's no macro cause effect power. The macro never beats the micro, and we end up saying there are no causally equivalent macro units, there's no systems of macro units that are causally equivalent to our simulandum. So because the simulands, the simulandum, the target system, and the computer can never have equivalent cause effect structures, we must conclude that they can never have equivalent phenomenology, equivalent experiences, and therefore, despite their functional equivalence, they are never phenomenally equivalent. So functional equivalence is not enough to guarantee phenomenal equivalence. It doesn't imply it.
On that side, is this essentially because like each of these units don't actually directly interact with each other, they're mediated by the multiplexer?
Yeah. So I'll give one comment on that. Yeah. So basically, when you're causally analyzing these units, you can't just pretend these units aren't there. They all have a job to do as background conditions, or mediators of effects, or they're all doing something. And so there's the point there is like you have to, what are you doing with this? Is it a part of these macro units, or is it a part of the background? And when you work through each of those situations, the conclusion is the cause effect power is not going up. To go through it in any more detail would totally derail the conversation. So, but I am willing to talk about it outside of this. Yeah. So a few more kind of results. So the computer's cause effect structure can be dissociated from what it's simulating. So I can create another 4-unit system. This is rule 110, the cellular automata. And here, the cause effect structures of my two targets are clearly different qualitatively, and the computer's cause effect structures are the same, right? This is just a different state of the computer, so it has the same qualitative cause effect structures. So not only is it not related to the function, but it's dissociated, or it's not equivalent to the function, but it's dissociated. And because I can do this with rule 110, I can also just proof by induction. I can make my computer arbitrarily large while maintaining the same modular structures and simulate an arbitrarily large rule 110 CA, which has been shown to be Turing complete. And so I can extend this computer to perform any function conceptually. And so this result holds regardless of the function being simulated. And so our target system of size n, its big phi is going to, its potential big phi is going to grow at 2 to the 2 to the n. So, double exponentially. Whereas my computer, when I make it bigger like this, I just have more lines of program and more monads in it. And so its total big phi goes up linearly with n, which, as everyone knows, is much slower than double exponentially.
Yeah, sorry, on the simulation part,
Yeah.
simulation doesn't really necessarily knowing that the whole effect structure will be the same.
So this cause effect structure, we show what it is. And because this computer can implement this function. And these two are function. This is a functional thing. So this can implement any function. Yeah, but this is the cause effect structure I'm talking. The one here that I can extrapolate. All right, so conclusion, being versus doing. What matters for consciousness is not what something does, it's what something is. And so this leads to this kind of double dissociation between consciousness and intelligence. So here's our kind of evolutionary hierarchy. This is kind of where everyone kind of has the intuition of consciousness. You know, up here is us and we're conscious, and there's the dogs that we all love, and would really, I also hope they're conscious, but that's my personal belief as opposed to my scientific view. And as we go down, you know, we kind of ascribe less and less consciousness to these things, but they're kind of in line with their intelligence. But we really talk about the off diagonals here. This is the computer, which is intelligent without experience. And this is maybe the brain organoid, which has experience without intelligence, potentially. Okay, so a few more prompts. So I've argued from the perspective of IIT that functional equivalence does not apply phenomenal equivalence. Some natural follow-up questions. Well, is it possible to realize the same phenomenology, the same cause-effect structure in two different substrates? You know, whether that's, you know, biological and silicon or what, but it's like could two micro substrates have different TPMs and nonetheless the same cause-effect structure? There are nuances to the process that could allow for that, but I don't know if it's in practice can be done, or can two different micro TPMs have the same macro TPMs and thus the same macro cause-effect structures? Can I multiply realize human phenomenology? And then according to IIT, there can be a dissociation between function and phenomenology. Can there or should there be a relationship within a specific context? If I say, okay, assume X, can I then establish a correlation between functions? So obviously within humans, we have this feeling of a relationship between function and phenomenology. Is there a way to kind of like build into that? And any assumptions in which we can establish such a relationship? Is it possible to have highly conscious computers? So I gave a specific example of a computer, which is fairly representative of like standard computer architectures. But what about different kinds of computer architectures? Obvious thoughts is, what about neuromorphic computer architectures? What about quantum computers? I don't know a lot about quantum computers, so I didn't write them. If such a computer would have hi-fi, what could it be like to be that computer? And would it necessarily be related to the function, or could it still be dissociated from its function while being highly conscious? All right.
That we go to restart again to the mark.
No, you only have a TPM.
You only have a TPM.
Yeah, so if you don't know anything about the structural connectivity, you could get messed up, right? So that is why you could have the same TPM for your simulation and the simulation. But the difference is the simulation has actual physical connectivity. There's a structure called the model that goes with it.
Exactly.
So, but the problem is that in Pi-Fi, you can just hand it.
It's on you to kind of justify that based on a physical reality.
Technically, you could fool Pi-Fi by just handing it a TPM.
It's done for sure.
So then what I had in my slide when I say if the system is fully described, what I really mean by this is you know there's a structured possible model. It's okay if you don't know what it is, but you have to make sure that it's
but you're not just kind of making it up in some sense.
Yeah.
You know, it's not based on.
It has to be.
If there was a physical system that was this TPM, then or physical system meaning structural comments. If there was a causal model that had this TPM, this is what it would be.
Exactly.
But if there's not, then that's just a calculation of complexity of a TPM.
Exactly, yes, so. No. But then how did he prefer that?
We like decompose it. Do it on the side. Yeah. That would be interesting.
And we open.